We've been building toward variable step size LMS algorithms for a while. In our discussions, I think it has become clear that having a large step size provides a nice, fast rate of convergence, provided it's chosen appropriately. But having a small step size can decrease the misadjustment error as we approach the optimal solution. Finally, we would like our step size to be responsive to changes in the signal, as we discussed with the normalized LMS filter. These three requirements can be met by various variable step size LMS algorithms. So here are some options. One, we could have that mu is equal to 1 over c plus n. In this case, c is a constant, and n is our time index. So formally, I guess we should move this over and now make mu a function of n. Okay, so when n is equal to 0, when we first start out, we will have a mu of 1 over c, and then as n increases, mu goes to 0. It might go to 0 a little bit too fast, though. So to provide a little bit more control, we can do 1 over c1 plus c2 times n. And this will make mu go to 0, well, faster or slower depending on how we choose c2, but usually we want it to be a little bit slower. Note that we may not actually want mu to go all the way to 0, in which case we can set mu of n is equal to the max of one of these functions and a lower limit. We'll just call it mu min. That makes it so that we keep converging always, or keep adapting, but perhaps at some minimal rate after we've originally gotten there. Okay, so all of these make sense for a stationary system, because in a stationary system we will have one optimal solution. Once we reach it, we just want to make sure that we stay as close to that as possible. In the case of a non-stationary system, we'll typically want to, we can still use this same thing, but we'll want to detect a change in the error and then increase mu or reset our variable step size back to some initial value. So there are advantages and disadvantages to this approach. First, I'll say that having looked at many systems that are deployed in actual applications in industry, this is not an uncommon way to proceed. Having the variable step size ensures that we're going to adapt quickly to cancel echo, for example, or feedback. And then as we clamp down on the mu, we ensure that our performance remains very good. So we're going to have kind of the best of both worlds, a low misadjustment error and a fast response. But back to the echo cancellation example, if we have, say, a speakerphone, a cell phone sitting on the table in speakerphone mode, if you move the phone or somebody nearby moves, the echo path changes. And if we have a variable step size, we might be stuck now with a very small mu and unable to respond to that change. So what will happen is we'll see a jump in the error that comes back. When that jump occurs, we simply reset mu to a larger value, in this case effectively reset the n in the denominator of mu, so that it can once again adapt quickly. There is a danger to this, and you have to know your application pretty well. And the danger is that that increase in error may come for another reason. For example, in the speakerphone example, double talk would result in a large increase in error. And at that time, we would not want to adapt our filter. So what is double talk? We'll talk about this more, I think, later in some applications. But the idea is that with adaptive error cancellation, we will send a signal out of the speaker, which will bounce around the environment and come back in through the microphone, and we want to cancel that. So our desired signal then is the signal as it comes back. The input into our adaptive filter is the signal that we sent out of the speaker. This might work better if I drew a picture. In this case, we have our speaker on the top, the microphone on the bottom, and we take our output signal. It is effectively the input into our adaptive filter. The microphone is the desired signal, and we want to cancel that desired signal or predict the desired signal exactly. So W should learn the current transfer function or impulse response of the room, the listening space in which those speakers, the speaker and microphone are located. And so we'll adapt W, and that should cancel things. If something moves and this path changes, then we're going to want to adapt W again to try to cancel this. Our ears are very effective, and we tend to compress the amplitude of audio onto a log scale. So loudness is a function of the log of the amplitude, which means in order to get good echo cancellation, such that we don't hear the echo, it has to be really good. And a lot of work has been put into making this work for telephone systems of all sorts. But what it comes down to is that we need to have a small misadjustment error, in other words, a very small mu. On the other hand, we need to respond very quickly when there's a change in the environment in the room, hence this variable step size. So we're going to monitor the error. The error as it comes out is actually going to be our desired signal. And where does the desired part of this signal come from? It comes from the fact that we have somebody in the room speaking, and that's being picked up by the microphone. Now, when somebody is speaking, we are going to, the error will then be their voice. That's the part that we can't cancel. However, our gradient estimate becomes very poor because we have what is effectively a very large signal added to our desired signal. So the weights start to bounce around and misadjust. So we want to detect when I didn't leave enough room for that. Let me rewrite that. I'll just put the word detect in there and explain it. We want to detect when the green man here is speaking and stop the adaptation of the filter. When he is not speaking, we allow the adaptation to continue. So we'll monitor the input signal and the output signal, and there are various algorithms that we'll do that are used to do this that we won't talk about right now. Double talk is when the person at the far end is speaking, so there's sound coming out of the speaker, and the person at the near end is speaking. If we try to adapt at that time, we're going to fall out of adjustment. So here's the problem with the variable step size. The problem is that if the error jumps up, we can assume one of two things happening. One thing is the feedback path changed, and we need to adapt. The other thing that could have happened is that somebody, this green man, started speaking. The error then represents his voice, and we don't want to adapt on that. So care is put into such situations. one of the tricks is to try to make the double talk detector efficient. When I first started studying this, that was a really big problem. Now there's more computational horsepower in my watch than we had in our early systems, so it's not as big of a deal, and double talk detectors are good. But we want to make sure that there's no double talk detect, but when we see the error go up, then we can reset our adaptation. There are other approaches to figuring out what to do. One of them involves having parallel adaptive filters. One of the adaptive filters is allowed to continue to update while the other remains temporarily fixed. If the error goes down for the updating adaptive filter, its weights after time, whatever that may be according to the application, maybe 10 milliseconds, maybe 20 milliseconds or a second, the weights from the adapting filter are copied into the frozen filter, and the frozen filter is the one that produces the output that matters, the one that will be listened to. The adapting filter always adapts. If the error goes up relative to the fixed filter, then the weights are not copied over to the fixed filter. In this way, we can have continuous adaptation, and we reduce the risk of becoming misadjusted due to other problems. Okay, so this type of approach, using mu is equal to 1 over some constant plus a constant times n, for example, it works well for stationary signals, as we've discussed, but for a non-stationary system, we have to monitor this and occasionally boot mu back up to a larger value by effectively resetting n and readapting. In some situations, that's hard to do. So here's another approach that gets rid of that whole issue, and that is we're going to monitor the sign changes in the instantaneous gradient estimate, E times x. Now, we can increase our mu if the sign is the same for multiple successive updates. What does the sign being the same mean? It means that we're a long ways from the solution, and we have to keep moving in the same direction to get there. Alternatively, if the sign changes frequently, then we can assume that we're pretty close to the solution, and we can decrease our mu. So we also want to put hard limits on what mu k can be. We don't want it getting too large, and we don't want it getting too small. And one thing to notice here is that we've introduced a new subscript to mu. That's k. K is referring to the kth element of x. So for this algorithm, we can actually have a mu that's custom to each delay tap. So if we have a particular weight that's way out of line, we can bring it into line quickly. Whereas if we have one that's really close, maybe it won't change as much. So what does this look like? Well, assume we had a system where our optimal, our target, changed over time. Maybe there's some change in the system. I'm going to approximate it just as a step change, although this would be maybe unlikely in a real situation. So what's going to happen to the weights here? Well, they will start out, maybe they start out at 0, and we'll see right away that we need to update. It's going to go over and it'll start to decrease. And maybe we'll come up with something like this. It'll be out here and it'll realize the error is way off, and so it'll update quickly and then narrow back in on the correct solution. Choosing the amount of increase or decrease is a bit of an art, but this is an effective way to do updates where we don't have to actually detect error. I don't know if I did a good job illustrating it right here. The problem is, if mu gets near its maximum value, it may take a little while for this update method to get it back down to where we want it. And so we'll have this overshoot. The advantage of explicitly detecting when we are now out of convergence is that we can reset mu immediately to an appropriate value.